attendees are in listen-only mode.
Good afternoon, everyone. This is Ritesha here from Red Hat. I am a senior solution architect, predominantly specialized on storage product line from Red Hat. I would like to thank you all for joining this webinar. And I know everyone is busy, having a busy schedule, especially during the weekday. So thanks a lot for joining in. And it's a pretty good attendee I had seen. So thanks everyone once again for joining in. This is more of Ceph and Gluster. There are two products which we have, and I wanted to have a comparative theology to take away in terms of what are the key differentiated points we have from our storage portfolio. I plan to have this for like around 40 minutes to discuss and put forward my thoughts, and then we'll have around 10 minutes to do Q&A. So there is chat window available as well. You can push your questions to the chat window, and at the end of the presentation I will address depending on the availability of the time. So let's get started. Something exciting is happening, we all know, in the storage industry. Every day the human race collectively stores more information than the day before, driven by computing, mobile computing, Internet of Things, and big data. Among the other things, this trend shows no sign of sleeping anytime soon. It is accelerating. The storage paradigm is changing, we all know that, right? So traditional storages are not flexible, they are purpose-built and create silos. In fact, they also do vendor locking. That's where the open software-defined storage comes in. It takes a different approach. By using open source software with standard servers and disks, enterprise can build flexible distributed systems to meet a variety of next generation storage needs. So this is where the idea of software defined storage comes in. So if you see the next slide here, it talks about software defined storage. What is software defined storage? SDS is where you can combine server based systems with bunch of disks, have it centrally managed, and control in an open system, open ecosystem. This not only leads to much more flexible distributed architecture compared to the silos, traditional storage vendors, but also provides the necessary performance for massive unstructured data storage, which traditional storage vendors are not able to provide. So if you see this slide, it talks about you have server-based systems which are centrally controlled, and it is an open ecosystem. So this is what software-defined storage is all about. So we see here server-based storage as on the right side compared to the left side, which are the traditional storage users. So like if you see the left side, there are three appliances with which bunch of storage, and users are all siloed on specific appliances. So you may have appliance for OLTP, you may have appliance for batch transactions, you may have appliance for web transactions, you may have different sort of appliances from storage perspective for storing different types of workloads based data. On the right side, what we try to do is to use software defined storage and create a distributed cluster of services which will be spread across multiple of these servers in a distributed fashion to not only give you the kind of performance you need, the agility you need, but also the efficiency which brings in from the overall manageability of the cluster and the scale out architecture which it helps to provide in future. It also takes care of the future requirements is what I mean. So as and when you keep adding, either you can keep adding compute or you can keep adding storage depending on what your futuristic needs will be in the same ecosystem in a distributed cluster on the right side, but on the left side you still need to have the complete storage being upgraded. For example, if you want to add a bunch of disks, you need to add controllers into the storage, you need to add front-end ports, you need to add back-end ports. Everything needs to be added to ensure that kind of a throughput comes in from that particular storage. So that's very different in a distributed cluster, because each and every node will participate in you getting the kind of performance you need for your specific workloads. Predominantly, unstructured data is what we are talking about here, and that's huge. I mean, what is unstructured data? It's data which is either in a PDF format, the documents which are in PDF, the syslogs, which are all unstructured. Then you have images and videos, and a lot of seismic data, graphs, and things like that. These are all unstructured data. Huge amounts of data are there. For example, video streaming. A 4 gig or let's say you are talking about the new technologies with 4K and 8K videos coming in. If you want to stream these videos on a traditional appliance, that will be choked. But if we have to have it on a distributed cluster, the video is spread across multiple nodes in an object format. So the data streaming becomes very fast because all the nodes participate in a distributed architecture. So that's the power of distributed architecture from video streaming perspective. It's the same concept for the other kind of unstructured workloads as well. The key advantage here is that you create this distributed cluster using commodity x86 servers with JBots connected to it. And the software will ensure that you get the enterprise reliability and availability and performance, which is required for your specific workloads. Of course, I mean, if you see in the other format as well, from the DevOps perspective, there is also a roadmap available for software-defined storage. You have a development model, you try to get into agility first, then you try to work to application architecture, get microservices in, then you get into deployment and packaging, get the container services running through the virtual services. Then this actually leads to a hybrid cloud, predominantly hosted in data center environments, and then you get into a software-defined storage, which can be a scale-up and scale-out model. So what happens is, for example, in one of the solutions which we have from storage perspective, I mean, we have containers which can run native Gluster, which is again a software-defined storage, and it can be a complete hybrid environment. Okay. And this is something which is a very unique combination which we have because we are talking about persistent storage here for containers. So we'll dwell a little deep in subsequent slides. So this is what we are up to. We are up to a disruption in the storage industry. Okay. So if this chart depicts how software-defined storage is much better than not only the traditional appliances, but also if someone is considering a public cloud storage, for example, Amazon S3, how a software-defined storage is better. It is better not only in terms of cost efficiency. I mean, software-defined storage, we are talking on-prem, on your premises in your data center. You create a software-defined storage for your workloads rather than hosting it on either traditional appliance or public cloud storage. And these are the benefits you get. You get better cost efficiency, better provisioning. We have fantastic provisioning tools available. So we have GUIs through which in the back end we can use Ansible to do huge amount of customization from the deployment perspective and ensure that it is optimally deployed. There is no vendor lock-in. Remember, all the Red Hat products are open source, and there is no vendor lock-in, and customer do have community versions available, which we also use to, from the upstream, we get it into our QA. We do a lot of enhancements in terms of the quality, testing, certifications, and then we release the specific products in terms of general availability and this release cycles. So there is no vendor lock-in here from our perspective. There is no. There is, in traditional appliances, there is vendor lock-in. In fact, in public cloud storage, is even more. You are moving hundreds of petabytes into Amazon. How are you planning to move that data back if you want to do it on-prem, or you want to move that data back for yourself? Even moving 1 petabyte takes weeks from Amazon cloud. So that's a huge vendor lock-in which is there from the public storage as well as traditional appliances. Skills required, of course, since it's on-prem, you need skills, but I mean, most of them have these skills. The thing is that most of them is open source. A lot of information is available in community, and Red Hat is of course there to help ensure that the skills are being updated for you. Governance, we have a very strong governance. Security is the key focus here. So right from your management framework to the storage, we have very good security built in. We have integration with the Active Directories which can be used from your corporate strategy perspective. You can have data invest encryptions. So the data, even if someone takes away the storage boxes, okay, your data it cannot be hacked. So from the governance perspective, public cloud is weaker, much weaker. Deployment options, there are very limited deployment options in public cloud. Appliances, traditional appliances also they are very limited because they are specialized for specific workloads. Software-defined storage, you can customize it depending on the kind of pools you make in your storage, distributed storage. You can actually have a broad deployment options available. So there is a good disruption happening here from the storage industry, and we are happy that we are in the forefront of that. And like I was talking about different kinds of storage available, the traditional storages are typically block storage and file storage. We all know what is block storage. It's a physical storage media which appears to computer as a series of sequential blocks of uniform size. Again, we use that to create file storage. Okay, so that's why you create file systems like XFS2 or ZFS or NTFS and things like that. So those are the file store specific storage. The new storage, which is an emerging storage, is the object store, where the object stores are distributed data algorithmically throughout a cluster of media without a rigid structure. So what object has is it has its own object ID, it has a metadata, and it has the data in it. And the metadata has details like what kind of data it has, what kind of permission it has, and how the data is distributed across the nodes. So if you see diagrammatically also, it's not having a very rigid structure, and the metadata can actually help you pull out the specific data which is distributed. For example, a video file will be distributed on tens of nodes, and the metadata will know exactly which specific nodes where data is to be grabbed, combined, and given it to the user. So that's something which helps you enhance throughput here. Whereas compared to the file store where that may not be the case, because sequential data access on file and block may be a bottleneck here because it's sequentially accessed, whereas in object store you can get the data parallelly accessed. So focusing on the file data as well as the object data, predominantly unstructured data, we have two Red Hat storage products. We have Red Hat Ceph storage and we have Red Hat Gluster storage. These are all open source software. Okay, each and every Red Hat storage product, whether it's Ceph or Gluster, it has its own. It has built-in Ceph. It has built-in management capabilities. It has built-in data service capabilities, and both of these products run on commodity or branded x86 systems like Intel, Cisco, Samsung, Dell, Supermicro, Fujitsu, Quanta. And of course, we have also worked with SanDisk and from the connecting their flash JBoards to x86 servers. We work with Samsung to have their NVMe based systems along with Ceph to get the kind of IOPS required. A 3-node Samsung NVMe Pro with Ceph cluster provides 700K IOPS. A SanDisk Infinite Flash we had tested which provides around 450K IOPS. So there are good reference papers available with all these architectures, whether it's Gluster or Ceph. So if you just Google it, you'll get all the reference paper for these specific architectures which I'm talking about. Again, on the right side, there are the key differentiators we have. We have share nothing scale out architecture, which provides durability and adapts to changing demands. The complete cluster is self-managing and self-healing. There is no very reduced, very less operational overhead here. So if there is a failure of a specific disk, the data gets relocated across the other disks to ensure that the data availability is maintained. Once you move the new disk in, you can add it into the cluster. Again, the rebalancing happens automatically. So there is very little operational overhead required here. From the shared nothing perspective, even the metadata is, we have the complete architecture is shared nothing. So that's why we are able to scale it out completely. The metadata is also spread across the nodes. So again, there is no bottleneck from the metadata perspective. For example, there are architectures with other providers, other software-defined storage providers or NAS providers where their metadata is confined into one or two controllers. And that's, so every time you access the data, you go to the metadata which is pertaining to a specific node only, and that becomes a bottleneck. What we do is our metadata gets spread across the nodes. So there is no single server serving metadata here. So either failure of that server leading to data unavailability is not a question. Again, if that particular node is choked because there are too many access to metadata happening from the frequency of data accessibility, again, we don't do that, so the performance hit is never a case for our storage portfolio, whether it is Ceph or Gluster. We have standard-based interfaces and full API ease integration with application and system. So you can use APIs to access and talk directly to the storage nodes. For example, in Ceph storage, we have APIs, lib API calls are made to the Ceph OSTs directly. So there is no intermediate layer available to actually pass on the data like the metadata. The data gets directly written into the disk or pulled out from the disk. So that so the latency from the network distributed architecture storage perspective is very minimal. And of course, there is the Red Hat backing in terms of experts supporting the complete ecosystem. So that's a huge benefit which you can get by leveraging the Red Hat storage products. Again, quickly, let me dwell into the Red Hat product overview, Red Hat storage product overview. So this one is on Red Hat Ceph storage. If you see on the left side, we are talking about a target use case. Red Hat Ceph storage is a powerful distributed storage for cloud and beyond. Not only does it integrate well with OpenStack, but it also can be a standalone storage in itself for your object and block storage. If you are doing if your requirement is storage as a service, especially object storage as a service, I mean, this is the best you can get, which can run on any hardware, x86 hardware, and can give you the best of the TCO and ROI. It is built from ground up as a next generation storage system. It's highly tunable, extensible, and configurable. The huge policy-based control can be provided. It has no single point of failure. And it offers very good interfaces for block, object store, and also APIs. If you see on the left side, it actually talks about what the target use case is here. One is, it's like I mentioned, it's for cloud infrastructure. All the OpenStack VMs for Cinder, Glance, Keystone, Manila, and Noah all can come from Ceph. With Ceph FS now, even the file access is available for OpenStack. So that's why we have all the features, all the modules of OpenStack which need storage coming from Ceph. Object storage for tenant applications, like I mentioned earlier, if you need to have a object storage as a service, again, this is something which you should look out for. The other use cases on rich media and archival, where there are many applications which are available which can do an S3 based compatible object storage. And for example, we have Convert backup storage, backup software, or a Veritas backup software. They do an S3 connectivity. So you can always use it to store to the backup or archival of your data onto software-defined storage. So that's that's kind of leveraging the S3-based APIs which we have on the Ceph storage. So similarly, there are applications which needs uh, to have connectivity to the Ceph storage with S3 based protocols, or with for RBD we have librd libraries available. So those things, those technologies can be used for your application to get connected to the backend Ceph storage. So there are a lot of ISVs, predominantly in telco we are working, who are directly accessing Ceph storage as a backend storage for predominantly in analytics space. Again, the highlight here is a reference for us. Cisco is a big reference for us. Not only do they implement, they have used Ceph storage for their next-gen cloud for themselves, but they are also we are also working closely with them to also have OpenStack Ceph storage based implementations along with Cisco hardware. There is a good reference white paper available with Cisco OpenStack Ceph storage. Do read out. I would recommend. It gives you good insights in terms of how you should have your OpenStack Ceph storage architecture with Cisco hardware. Okay, next is on Red Hat Gluster storage. Again, it's so like earlier I said with object storage, Ceph. For example, if I move back a slide, Ceph storage, you can think it as a distributed storage for cloud, predominantly object storage. Coming back to Gluster, you should think this predominantly as a file storage for unstructured data, predominantly used for OpenShift. So I'll explain a bit about OpenShift soon in a subsequent slide. So the idea of Gluster is to have an agile file storage with petabyte scale workloads. So we can go up to 100 of Gluster nodes, and the files can be distributed across these nodes. So the metadata also gets distributed across the nodes. And again, it's the same concept. Your metadata gets distributed, you don't have a single choking point in your environment from the throughput requirements. Something like HDFS is not able to do. So HDFS has the Hadoop data file store. It has a metadata server, and beyond a point in time, the HDFS starts to crawl because the metadata gets started choking, depending on the kind of throughput you need. So that's where Gluster can really. So similar kind of workloads, similar kind of metadata issues are avoided by the Gluster architecture. Again, it's a purpose-built scale-out file store. It has a very straightforward architecture. It can be integrated so that you can have some set of data in your on-prem. You can have it in cloud. You can have a Gluster in cloud, or you can have a hybrid as well, where some of the data is here in on-prem and some of the data gets into cloud. So very flexible for you to leverage whatever is the best issue you get. Simple to install and configure with minimal hardware footprint required. It offers mature NFS SMB interfaces for enterprise. If you, for example, this is something which you can replace your NAS. Again, if you see the target use cases on the left side, there's a container native storage. One of the key features here for Gluster, it provides containerized storage, it provides persistent storage for your containers. So very, very key important feature, and world is moving towards containers. So this is the storage which should be underlying for all the container environments which you are going to have, whether it's from Atomic, Red Hat Atomic, or whether you are having some other containers or Docker or things like that. It does enterprise file sharing. You can have media streaming, you can have active archives, very good use case. You can have huge amount of servers with good capacity of disks for cold archivals, and just keep moving the data in for years and years. For example, the tape drives, customers are having compliance or regulations from the government to store data for 7 years, 10 years, or for ages till they survive. Now tapes, if they have to retrieve at time, for example 5 years down the line, either the tape technology has changed, or they are not able to have the drives available, or the tape is not working. So the retrieval cost becomes very costly. And of course, technology keeps changing, right? So you always have to keep moving your data into new technology-based tape drives. So that's where the software-defined storage also helps, because even if you keep changing the underlying x86 servers with JBoards, the layer of software is not changed here. So there is no impact in terms of your data, and you don't have to have any operational challenges. Again, it is a seamless migration into your new environment. So you can keep phasing out your older hardware while you keep adding into the new hardware without disruption to your storage. So huge benefit, huge investment protection you have. Again, an example here is to give is an Intuit uses Red Hat Gluster for flexible, cost-effective storage for its financial offerings. So that is a finance-based reference for you. And again, this is Gluster I'm talking about. So these are the two products I have. Now let's try to dwell a little deeper in the use cases. For example, Ceph. This is the Ceph is predominantly for OpenStack, and Gluster is predominantly for OpenShift. With the kind of modules we support, Keystone, Swift, Cinder, Glance, and Nova. Okay. If you see the bottom line, there is Red Hat Ceph storage available, and the Keystone and Swift can be connected to Red Hat Ceph storage using Ceph object gateways. Nova can be connected through OpenStack hypervisor to the Red Hat Ceph storage. So these, so hypervisor has built-in capability to go and talk to Ceph storage here, the OpenStack hypervisor which we have. Cinder and Glance, they directly communicate to Red Hat Ceph storage. So this combination which we have is what we have ensured that it is being it is being combined at the engineering level. So the OpenStack engineering guys and the Red Hat Ceph storage engineering guys are talking to each other, ensuring everything is working, QA is done properly before things are being released. So the other advantage of Red Hat Ceph storage is that you have near about instantaneous booting of hundreds of VMs simultaneously without really having to be choked in terms of your VM booting. So for cloud providers, service providers, or companies who needs to fork instantaneous VMs, right, and many of them together, and this is the solution you should be looking for. It supports full VM lifecycle through Glance, Cinder, and Nova. It has multiple I/O service levels within a single cluster, and we can also have multi-site configurations for disaster recovery or archiving. Okay, for Gluster, like I mentioned, OpenStack is with Ceph storage. OpenShift is with Gluster. So OpenShift is a DevOps. It actually gives you the complete DevOps environment, and all the containers we see, we can have multiple nodes here. Node 1 is having its own Postgres container without any cluster in it. We have node 2 and 3 which has containers and which also have cluster storage. So all the disks which are being seen in node 2 and 3 can be given along with the node 4 as a single cluster storage for all your container requirements from the storage perspective. So this not only offers lower TCO, but it's a unified orchestration, so which can be, so OpenShift orchestration itself can actually help you orchestrate the complete solution, like provisioning of containers, getting storage provision for that specific container, and then binding that specific container to a particular volume in the storage. So, and then giving the VM instance for the developer to start running their and testing their applications. So it's a huge ease of use. So the developers don't have to go and ask a storage vendor, a storage admin, please give me some storage. I mean, they have something which they can directly provision and start using it. And also gives them greater control. So this is Gluster for container native storage. Gluster uses something called as elastic hash algorithm. So that's why we don't see any single point in terms of choking or single point of failure. It's suitable for unstructured data stored. It uses elastic hashing. So files assigned to virtual volumes and they are assigned to multiple bricks, and volumes easily are reassigned on the fly. Location hashed on the file name. So a client, if it asks for a specific file, it is hashed onto a specific node. So it knows exactly which specific node the data is to go and retrieve. So there is, so it's huge improvement in terms of latency for accessing or retrieval of a specific file compared to other NAS storages, storage solutions available in the market, including distributed storage. So that's why there is no performance bottleneck, and it eliminates risk scenarios also. Similarly, again, this is talking more of Gluster again, where it does a distributed volume. So the data gets uniformly distributed across all the bricks in the namespace. So that's why there is no single point of choke in terms of performance as well as in terms of availability, because the data gets replicated also. Similarly, in Ceph, the data also gets placed in such a way that it's balanced across the cluster with the help of an algorithm called crush algorithm. Now, there are multiple things which we support in Ceph. We support replication of the data and erasure coding of the data. This helps to ensure that the data is always available. For example, object store, we can either have replica 3 copy as depicted on the left side. So 1 copy, 2 copy, 3 copies. So same data is replicated twice. So it gives you very high durability and quick recovery. On the right side, we have erasure coding, where it's something like a redundant array of inexpensive nodes. So you have 6 nodes, the data is spread on 4 nodes, 2 nodes are for parity. And the erasure coding algorithm ensures that data is distributed and parity evenly across the nodes. So this is 1 copy plus parity, and we can have an n plus m algorithm where n is the data chunk and m is the parity chunk, and that will define the availability of the data. It is expensive recovery though compared to the replicated pool which we saw on the left side, but huge saving in terms of cost from the TCO perspective. This is something which a lot of customers have started adopting, especially for cold archivals and few retrieval scenarios. Gluster, fault-tolerant data placement, like we saw in Ceph. We have replica as well as we have erasure coding. Here also, this is a replica functionality. So it's a distributed replicated volume. So the data gets spread across 2 bricks which are on 2 different servers. So for example, file 1 is on brick 1 and on 2 bricks on 2 different servers, which is a replicated volume 0. Then there are again 2 servers doing the second file store. So again, that is also a replicated volume on those 2 servers, and all these 4 servers will actually form a distributed replicated volume. So the data will always be stored twice here. So it's like one server 1 is having data, and server 2 is having the mirror copy of that. Retrievals will happen from either of the servers. So you again get the read throughputs are very, very high here. So this helps you create a fault-tolerant distributed volume by mirroring same file across 2 bricks. And then you can keep scaling this. So server 5.6 will be for replicated volume 2, server 7.8 will be for replicated volume 3, and so on and so forth. That will become a distributed replicated volume. Again, on Gluster also supports erasure coding like Ceph does. So the data can get spread across 4 bricks, and 2 bricks can be for parity. This is what is called as a dispersed volume in Gluster terminology. Moving on to site-specific replications in Ceph multi-site. For block storage, we have something called as a RPD mirroring. RPD mirroring ensures that whatever is being changed in a block device gets replicated across site in an asynchronous format, so that that data is also available on the DR side. So this is predominantly a DR requirement which will fulfill this specific aspect. Ceph multi-site for object is also available, so we can have 2 different clusters, Red House clusters or Ceph clusters across 2 different sites, and they can be master-master. So both of them can be active at the same time. You can use global load balancers, for example, in content delivery network, and the data, depending on the locality of the user, the data can actually be written or read from that specific cluster. And you can either sync only the user space, or actually sync the whole data depending on the availability of the network and the requirement you have. Okay. Again, on the Gluster front also we have geo-replication. We have different type of replication in Gluster. Again, it's async replication. So we can have one-to-one replication, we can have one-to-many replication, and we can have cascading replication also. It can be a continuous or incremental replication. We have master-slave model also available here. As I mentioned earlier, it's an asynchronous replication. It can be over LAN, WAN, on internet, depending on the RPO or RTO requirements. Okay, coming back to the client access, we have, many protocols are being supported on Gluster, including Swift Object Translator. So Gluster can not only read and write for you in terms of SMB, NFS, or API calls, it can also do object for you with Swift. So any specific requirement you have where you have predominant file-based workloads and some amount of object-based workloads, you can definitely look for Gluster as an option. It also uses Gluster Fuse, which is high-performance access to the Gluster files from the client perspective. So these are the protocols which you support, and of course you can either have it hosted on-prem or you can have it hosted on public cloud instances as well if you need to. Or you can have a hybrid of it. Similarly for Ceph, we have three different modes here to access the storage like Rados. We have for object store, we can use Rados Gateway, RGW, which is again a web service gateway for object store compatible with S3 and Swift. So any application using S3 and Swift can connect to Rados using RGW. We have RBD for host VMs, again which is a reliable fully distributed block device with cloud platform integration. For example, in OpenStack scenario for the VMs. The third one is clients who need CephFS as a file system access. It's a distributed file system, provides POSIX semantics, and it's a scale-out metadata management. Okay. We also have a library which can be used to access Rados, which is the underlying Ceph storage, using either C, C++, Java, Python, Ruby, PHP, or embed in your applications. Again, bottom line, it's Rados, which is again a reliable autonomous distributed object store. The self-healing, self-managing. It's a very intelligent node, storage node, and it's very lightweight. So that is what I had in terms of the differentiators which we had, like for example, we have bit rot in both the products, Gluster and Ceph storage, where the data it actually then scrubs the storage. There's a light and heavy scrub, and depending on the bit flips, it will ensure that the bit flips do not happen, or it reverses that so that the integrity of the data is always maintained. Especially important when the data is images, videos, and high quality graphics data. So very, very useful feature, which is very rare in terms of the other storage, software-defined storage providers available in the market. So this is where I wanted to end in terms of just leave this thought. You can go ahead, do yourself register for the test drive. So we have test drive available for Ceph storage and Gluster storage. It's a very well documented lab available online, and it's free for you to use. So you can go do a test drive, do a deep dive in either Ceph storage, Gluster storage, or both. Learn how it's easy to implement, and it doesn't take more than I think 2 hours for you to complete one lab. And I mean, you are all set with Ceph storage or Gluster storage. So that's that easy. Okay, so I'm almost 45 minutes up, and I just wanted to see if there are any questions so that I can start addressing the questions, if any. Let me see the chat room. Okay. So as of now, I don't see any questions. There are still 60, I mean, there are quite a good number of attendees still online. Okay, I'll wait for a minute to see if there are any questions coming up from the users. Okay, there's a question on specific examples of block file and object store. That's a question being asked by one of the attendees. Okay, so yeah, I mean the examples for file would be predominantly your network attached storage or your POSIX compliant file, like you create an XFS file system and the data which resides on that file system is the file form based data. Now underlying block storage is always, for example, in Oracle database, you use directly expose the block data without creating any file structure on top of it. So that is an example of block store. The other is where you actually boot your data, right? Boot your VMs or OS. That again needs block storage. Object store, it's all examples of object store would be mostly in the, for example, we do S3 connectivity to your Amazon, right? That data gets stored in object format. Your video streaming data either can be in file format or object format. So these are some of the examples. Okay, I hope I was able to answer your question. Okay, the next one is, are these benchmarks against EMC or other drives? Okay, so we have published the benchmarks. We have published some of the performance numbers, and these are not against the EMC drives. These are something which we have tested using the standard tools available to test and publish the same results. So I think most of the time EMC do not publish their results, performance results in any case. So no one knows how their benchmark results are. But again, they also don't have their specific benchmarks available on the object store as well, whereas we are able to publish it with the help of, along with Samsung, we have been able to publish the IOPS and the throughput which are being provided on Ceph storage. So we have used 3 Ceph storage Samsung nodes with NVMe on it, Intel nodes with NVMe, and we're able to provide around 700K of IOPS. There are other results also available, like traditional JBoards connected multiple node storage, distributed Ceph or Gluster storage. Throughputs are also being provided. Those papers are also available, reference papers. Okay, is there any mechanism to avoid file locking like DLL? I mean, for us, if we see from the NFS perspective, we get through the metadata. So the data gets accessed, metadata is also spread, and the data is also spread in Gluster. So whenever the data is accessed, locking will always be there, okay? And but what happens is reads are not locked. So only when there is a write to be done, if the data, only then a locking happens. But since it's a distributed architecture, but anyway, you can't avoid locking from the file perspective. The locking has to be there, otherwise there is a chance of data not being clean if there are multiple modifications being done at the same time. But there are good developments happen from that perspective, which we have incorporated to ensure that the lockings are being taken care of rather than file level at specific segments of the files. Okay, can I use Gluster instead of pacemaker cluster? Okay, nice question. So see, we have in Gluster, it's predominantly a storage, whereas pacemaker cluster, you will actually be running your applications and the applications will fail over onto each other. So Gluster in the backend, if you want to have an NFS, highly available NFS environment, instead of pacemaker, based NFS highly available environment, you can go with Gluster with NFS Ganesha. So that's a highly available Gluster environment, and it will ensure that the NFS services are available upon a node down. Okay. So that is something which definitely can be looked upon, but it is not a replacement for pacemaker cluster. Okay, who are your competitors in this space? I mean, there are many competitors depending on how we look into it, like EMC, Hitachi, then IBM, they all have their own software-defined storage products now. Even the traditional vendors have started exploring software-defined storage now. And there are others who are new players also, like SimplyWithy, Nutanix with their hyperconverged. So there are different set of solutions and different set of customers in those spaces. Like in object store, there are other software-defined storage providers also available. Okay, like where the next question. Okay, like where the object storage will be used. So object storage will be used where you want to have your object. For example, you want to use the RESTful based API. Like example is Dropbox solution. Everyone knows, everyone uses Dropbox. So if you want to have your application running on mobile, you just move the data onto a drive, Google Drive or Dropbox. Okay, that data gets, that particular PDF or image gets directly saved in an object format using RESTful APIs. So that's a good use case from the object perspective. So the retrievals are also very fast, and because there are millions and millions of objects, for example, Facebook, okay, or Twitter. So that's why the distributed architecture really helps to not only write the data but read the data very fast. Okay, will the presentation be shared? Is a question here. Okay, I mean that is something which our communications team will be able to take care of. Okay, next. Okay, there is again a question on can you please detail a use case how Ceph storage can help a media and entertainment industry sharing data on cloud? Okay, so now this I assume that is an on-prem cloud where we are trying to create a cloud environment for other media and entertainment customers. So what you can do is you can actually create a Ceph storage cluster with your own application which can actually be a front end for your media and entertainment, and that data can be accessed using the APIs which we provide. One example is content delivery. Let's say you have multiple, let's say you have Delhi region, Mumbai region and Chennai region, and you want to do a content delivery for your users from the video streaming perspective. So depending on where the user is, a global load balancer can actually divert that user to that specific locality to pull the data and stream it. So that is one use case which we see. The other use case is where the data needs to be converted into multiple types of file formats and to be stored. Again, that is the other use case which we can have, and all this data can be on Ceph storage. Yes, I agree. I mean, there is one more question on hosting media and sharing the same. Yes, I mean that is also one of the good use case available. Okay, there is considering disaster recovery scenario between Ceph and Gluster, which would be ideal for data recovery that goes to a point in time. Okay, how is versioning achieved with these storages? Okay, that's another question. Interesting questions. So Ceph and Gluster storage, I mean, both are able to do an async replication across the sites. Okay, and both can have snapshots available, and you can have local snapshots available, and you can replicate as well across sites. So, I mean, there is no difference in terms of the data recovery perspective. Okay. Versioning is achieved, I mean, we can have a built-in logic from the application perspective, so wherever there is a change, it actually keeps map of the specific file. It keeps a copy of the file as a version change and moves on to and writes onto a new one. Or you can also do snapshotting for a point in time copy. Okay, does this support storage tiering based on content? Storage tiering is one of the options which is available. Like for example, in Gluster we can have a hot tier and a cold tier. Hot tier can be with SSDs, and you can have cold tier with SATA or SAS disks, NL SAS disks. And based on content, I mean it will be based on the hot data and the cold data policies. Depending on content, the application needs to then decide. So you can create separate pools at the storage tier. I mean, at the storage level, for example, you can have an SSD pool separate. You can have a SAS, NL SAS pool separate, and application can actually decide what kind of content is there to write to which specific pool. So that logic will have to go upwards because the cluster storage tiering it works on the hot and the cold tier, and it works on the data accessibility or the time or specifically how much time that specific file is being accessed. How different you are from Nutanix? Okay, interesting question. I mean, we are open source. Very important. You don't get vendor locked in. But I mean, I don't want to get deeper into the comparisons, but I put forward the features which we have. I mean, we do have complete hyperconverged infrastructure available, but the advantage we have is that you can use any of the x86 hardware vendors, whoever gives you the best pricing, to put our software on it. It's a completely integrated software stack which we have, whereas Nutanix only has the management layer. The other layer, like the hypervisor, comes from others. Okay, so they don't do an engineering level integration which we do. So that's a very good advantage which we have compared to Nutanix. Okay, are we going to provide solutions for structured data too in near future? See, we are going to have some of the iSCSI support, but purely from the point of view of specific VM requirements, where the VMs needs to be booted through iSCSI. For your specific question on structured data, we already have, we already do support some of the databases like MySQL in the structured data as well. Predominantly on Ceph storage, we're trying to create good use cases, especially with OpenStack environments, where the database can be MySQL running on Ceph storage. So we do have structured data availability right now as well. But we still don't want to get into the OLTP space because our function, our domain is unstructured data, and that's something which is growing massively. So that's what we plan to serve and cater to the customers. Okay. Whether SDS is compatible with different VMS available in the market. This is what I mean, video management surveillance. See, from the perspective of VMS, the VMS application vendor, if they are able to write and do a POSIX or a file-based access, whether it is on a file system or on an NFS mounted volume, I mean, we should be able to help support that. So that should not be a problem. But that answer, I think, will have to be, we have some of the VMS folks who works with us, and their stack is also certified. I mean, it's not certified, but it works, is what being tested by both of us. Okay, how Ceph storage can be recommended for backup as a solution? Is a question here. So yeah, Ceph storage, see, if you have large amount of unstructured data which you need to be backing up, you can use Ceph as a backup option, because Ceph provides an S3 connectivity, API connectivity. So your software, backup software like Veritas or Commvault can actually use that API to move this data from your application or database or wherever the data is, and move that into your Ceph storage. So that is possible, and that can back up any set of data, whatever is being supported by your backup software. Does Nutanix have the layer called Acropolis? What is the layer you have and is called? I mean, really, I would not like to get more into Nutanix, but would like to restrict ourselves on the products which we have. So Ceph is used in big data analytics use case. Why is Red Hat preferring Gluster for analytics? I mean, it purely depends on what kind of analytics software is running. You can use either Gluster or Ceph. Either of that is a workable solution. If it's a file-based access for analytics, Gluster is preferred. If it's something where you need a block device access, for example, some of the use cases which we have are block device access from the application perspective, then and it still needs a distributed architecture underlying, then Ceph is something which is preferred. So there are differences, and both of them work in the analytics space. Okay, what are the means of accessing a Ceph storage? CLI, GU, IP, hostname, etc. So as I mentioned, last I think second last slide talked about how the data is being accessed with Ceph storage. So either you can use a Swift-based or a S3-based API. So the access is through RESTful APIs. The GUI is available from the manageability of the Ceph cluster. Okay. It is not based on hostname or IP address. The accessing is not based on hostname or IP address for Ceph storage. It directly uses the librd protocol. So basically, let's say for example, if you want to connect a block device through the RHEL, if the client is Red Hat Linux, it has librd protocol. So librd will go and connect to the Ceph storage using the librd access mechanism. If it is S3 or Swift, it will be able to use the S3 or Swift API to connect to the Red House gateway using Red House gateway. Okay, what is the interface? iSCSI, FC, FCOE. So the interface here is all your normal TCP/IP. So that's the unique advantage you get because the interface is like FC. It's something which is not moving beyond 16 gig right now, whereas the Ethernet we are talking about is 100 gig. We have worked with Mellanox for 40 gig and with low latency non-blocking architectures, even on Ethernet. So there is a white paper available with Intel, Mellanox, and Red Hat storage. Okay, in terms of how we have leveraged TCP/IP network with 40 gig to achieve the kind of performance which even the fiber channel iSCSI will not be able to provide. Okay, one is on software-defined NAS box. I mean, Gluster also fits into a NAS category, so it does a lot of NAS functionalities, of course. Not for Ceph, but the additional thing which Gluster does is also has a connectivity to Swift and API connectivity for applications to access the Gluster storage directly, which is not the case with NAS boxes. So the flexibility is limited with NAS boxes compared to the software-defined storage offering which we have. Okay, I have already covered the backup piece. Do you support Ceph Gluster across multiple OS platforms such as okay, see the client, Gluster can be an NFS mount on either Solaris or AIX also. Okay. Now, the OS platform for this, so for the Ceph or Gluster, for Ceph we support RHEL and Ubuntu for the Ceph cluster, and for Gluster we support RHEL as the base operating system. We don't support Solaris and AIX. Okay, can you migrate existing legendary storage to Ceph storage and back? What is the effort involved if it is possible? Yeah, see, there needs to be a discovery workshop to be done to understand the kind of storage currently being implemented at your premises, and then we should be able to help answer this question to you. It's more of a discovery to be done, understanding how the architecture currently, what kind of data you are storing, how the data being accessed, and then we can decide on how much the effort is required to move in and out of a set for the cluster. Okay. So that's it. I think we are done with the questions, and I would like to thank you all for participating and taking some time out. Do try the test drives which are shown here, and the Ceph test drive and the Gluster test drive, and hope you enjoy it. Thank you.